Okay, so yeah, over dynamic, of course, is also closely related to many CMC methods. So in particular, unadjusted non-reversible algorithm and Metropolis adjusted non-reversible algorithms, not just discretizations of this, but even if you look at random walk Metropolis, there are relations because it somehow, although it's different, it somehow also is to a certain extent behaves such a process. Well, overland Langevin, the generator is the Markov process is this generator here. Since it's reversible, the generator is.
Yes, on the microphone, you have to raise your voice even more.
Okay, is it working? Thanks. Okay, so since the process is reversible, this generator is a symmetric operator. And so you can also look at its Dirichlet form, which is just the quadratic form corresponding to it. And this is very easy. This is just this 1/2 integral nabla f nabla g d mu for overdamped Langevin. And then well, in the reversible case, there is a clear notion of what the relaxation time is. This is not so clear in the non-reversible case. There's only one possible definition, I would say, for the L2 relaxation time, and it's just 1 over the spectral gap of the generator. And the spectral gap is also the best constant in the Poincar inequality. So it's equal to this infimum here. Infimum of the Dirichlet form over the variance of f. Okay, so that's all very well known. Now, what is the problem with this? The problem is that since this motion is diffusive, it's also somehow slow. So, for example, take for the state space now a torus of side length L. Yeah, and then assume your potential is uniformly bounded, could be even 0. If it's 0, you just have a Brownian motion. And then your relaxation time will be of order L squared, where L is the side length of the torus. Yeah, so it's rather slow because it has this random walk type behavior. And similarly, if we are on RD and say we are strongly convex, but we have a lower bound on the second derivative of the potential by a constant m, and this constant will usually be small, then the relaxation time will be bounded by 1 over m, and this bound is also sharp in the Gaussian case, which is also, again, diffusive behavior. So this constant 1 over m, even in nice scenarios, can be small. And if you look at discretization, then this leads to some condition number dependence, because then for the discretization, you will also need an upper bound for this quantity. And then relating the two, you get some condition number dependence in your bounds. And so then the question is, can we improve on this? And then the idea is to move to non-reversible Markov processes. And we have seen in the last, I don't know, 10, 20 years, a lot of advances going in this direction. And so the idea is you can now look at an extended state space. Well, you could also do it on the same state space, but it's somehow more practical to move to an extended state space where you have a position and velocity. And so RD times RD, so both are in RD. If you're on a manifold, this would be the tangent bundle of the Riemannian manifold. And then now you have an extended measure, which in the first component is just your original measure. And then you can, for example, take a product measure and just take a standard normal distribution in the second component. And then you have a measure on position and velocities, and the densities is just e to the minus h of xv, where h is the Hamiltonian. So it's just u of x plus 1/2 v squared is written here. Okay, and then there are actually several natural dynamics that leave this measure invariant. And the easiest one is just Hamiltonian dynamics, so just Newton's equation of motion. Because if you take derivative of position is velocity, derivative of velocity is minus the gradient of u evaluated at xt, then this is actually a Markov process, a deterministic Markov process, and it leaves this measure invariant. So this is the generator of this Markov process. It's now a first order operator because it's a deterministic Markov process. You just have an ODE. However, this process is not ergodic, which is quite clear because you know that the total energy is preserved. So in this case, H is preserved. So that means your process only moves on this level sets of your energy function on phase space. And so it's not irreducible and not ergodic. Okay, so to make it ergodic, you have to add some noise. And then what you do is you add some noise in the velocity because you want to avoid the random walk behavior. So you add it in the velocity, not in the position. And you can do that in various ways. The easiest way is maybe you wait for some exponentially distributed random time, and then you draw a new velocity uniformly at random. And that's what is called randomized Hamiltonian Monte Carlo. So you would just move like this, wait for an exponentially distributed time, then choose a new velocity, maybe this one, then move here, choose a new velocity, move here, and so on. Yeah, and so in that case, the generator is this one here. So here pi v is pi v applied to a function f is what you obtain if you integrate out the second variable with respect to the normal distribution. Okay, so that's one possibility of adding noise. Another possibility is what you do for Langevin dynamics. So Langevin dynamics, you include, so you look at the diffusion process and you include some Ornstein-Uhlenbeck noise in the velocity variable. That means you include a damping term. So you have a damping term here, and you include a term driven by a Brownian motion. And this is done in such a way that the same measure is still invariant. Okay, and then one observes that this really can accelerate things. So for example, if you look at the Gaussian case now, so just take your quadratic potential, mx squared over 2, then you can compute the spectral gap exactly, and it's plotted here. So gamma is now the friction coefficient. So this is a parameter you can choose. So for any choice of gamma, you have the right invariant measure. And then you see if you choose, actually the spectral gap is first increasing and then decreasing again. And if you choose gamma in the right way, which in this case means you have to choose it proportional to square root of m, then you actually get a spectral gap of order square root m, whereas before you had m. So you've gained a square root, you've gone from m to square root m, but only if you choose gamma in the right way. And so we have two regimes, the underdamped and the overdamped regime, and the most rapid mixing occurs at the boundary between these two regimes. And the overdamped Langevin dynamics is somehow what you get in a limit here if gamma goes to infinity. So this is somehow the classical reversible case. Okay, so that means we can get a diffusive to ballistic speed up also in these cases. And so now our questions are, well, what is the relation between the first class of processes like overdamped Langevin dynamics and the second non-reversible processes? Of course, there's a classical relation, which is this overdamped limit. If you go with gamma to infinity and do an appropriate rescaling, then it converges to this overdamped Langevin dynamics. But that's not what we want to look at. We don't want to go with gamma to infinity. We want a fixed gamma. And then we ask, how is the process at a fixed gamma related to the reversible process? And what we will see is actually that all these processes can be thought of as lifts of the same overdamped Langevin dynamics. So all the dynamics I presented to you are actually lifts of the same overdamped Langevin dynamics. And the overdamped Langevin dynamics is the converse. It's called a collapse of these processes. Okay, once we have understood that, then what consequences does it have? Well, we can learn something about the relaxation times from it. So what we actually can do is, now one can very easily give a lower bound for the relaxation time of any lift. So that means there's a limit. You cannot improve more than in a certain way by doing a lift. And the maximum you can improve will actually be you can gain a square root. So for Markov chains, there has been such a result. Now you can also get such a result for diffusions. Okay, and that's a quite important question because a lot of people have thought about can we do something better now that we have got this improvement using HMC and so on? Can we still do it better? Actually, we also thought about this for some years. The answer is no, because it's all lifts and you can only get this improvement by the lifts. And then once you realize this is then you can ask, can we at least achieve the optimal lift given by that, the optimal gain given by that bound? So can we get a maximal speed up? And that's a more difficult question, which requires an upper bound for relaxation times, but this framework also helps us to understand this question better. Okay, so now I can really start with the topic. So what is a lift? And now we start again very elementary with Markov chains, and then we try to see how we can generalize things from Markov chains to other processes. So lifts of Markov chains. So here is the classical example by Diaconos, Holmes, and Neal. It's very simple. You just have a discrete circle, and then you have a random walk on a discrete circle, which moves with probability 1/2 to each side. And now what is the lift of this process? For this, you consider two disjoint copies of the circle, which are, you can think of on top of each other. And then on one copy, you only move to the right. So you move to the right with probability 1 minus gamma. And on the other copy, you only move to the left with probability 1 minus gamma. And then with probability gamma, you change between the two, you switch between the two. And yeah, it turns out that this is a lift of this random walk here. And if you choose gamma in the right way, then the relaxation time improves to the square root. Okay, so more generally, we can look at the following. So we have a state space S hat, which is a product space, S times another space V. So V is our space of velocities. And then you have a measure on S hat, which is, well, can be a product measure, but can also be something which depends in the second component on the first. So in the first component, it's our measure mu that we're interested in. And then you have some kernel going to the second velocity component. Okay, and now we are given a transition kernel P with invariant measure mu on the space S and a transition kernel P hat with invariant measure mu hat on S hat. And then here is the definition of a lift. So we say that P hat is a lift of P if the following holds. When we start at xv, and we look at where we move to in position, but we take all velocities. So here we take the full velocity space. So we look at just where we move to in position. And then we average this over all initial velocities, averaged with respect to this measure kappa. Then we recover the kernel P. Okay, so this is the definition. And here's a warning. So this does not imply a corresponding relation between the n-step transition kernels. It's just about the one-step transition kernel, but the n-step transition kernels can be completely different. That's important to realize. So it's just about the one step. So for us, when we move from discrete to continuous time, this will mean that lifting is really an infinitesimal property. So it's really just about one step in discrete time. Okay, so now before we go to continuous time, let me rewrite this definition of lifts in some equivalent ways that will be useful when we go to continuous time. So let's call pi xv just the projection on the first x variable, position variable. And well, then the first thing we can do with this lift definition is just instead of writing it with sets, so if we go back here, we had this definition here. Instead of writing it with the set A, we can of course think of this as an indicator function of the set. So P applied to the indicator function of the set, and then replace the indicator function by a general function that's equivalent. So then that means we can write it in the following way. So we apply P hat to a function f, which only depends on x. So pi is the projection on x. And then we integrate the result with respect to kappa. And then we get the transition kernel P applied to the function f evaluated at x. Okay, so that's a simple rewriting. But once we have done this, we can also realize now that we can multiply both sides with another function g and then integrate. And then we see it's, and when we integrate, now integrate with respect to mu. And when we integrate this with respect to mu, we get the measure mu hat. So then it's also equivalent to this one. The integral of p hat of f of pi g of pi mu hat is the same as the integral of p f g d mu. Okay, and then we are almost there writing it in terms of the generator, because it's an infinitesimal property, we should be able to write it in terms of the generator. So because the generator of a Markov chain is just the transition kernel minus the identity, and so we can also rewrite it as the generator applied to f of pi times g of pi integrated with respect to mu hat is equal to the integral of LF g d mu. And this is just our Dirichlet form, so minus our Dirichlet form. Okay, so that's just an equivalent way of rewriting the old definition of lifts of Markov chains. And we call this a first order lift because in a moment I will introduce a second order lift. Okay, so now how can this be generalized to continuous time? This turns out to be not completely straightforward. Okay, let's again look at our simple example. Our simple example in discrete time was the random walk on the circle, on the discrete circle, and then we lifted it. Let's do the same here. So now we have Brownian motion on a continuous circle. And then when we lift it, we could take now again velocity +1 and -1. That would be a possibility. But let me take now all real numbers as possible velocities. So then we do not have just one copy of our circle, but infinitely many copies. And on each copy, the process is running with a fixed velocity. And so now what's going on is the process is just running with a fixed velocity for some time. And then we do a velocity refreshment and move to another velocity. And then we move with this velocity for a fixed time. Then we again move to another velocity with this one, and so on. Yeah? So that should be a lift. Actually, what I have here is just randomized Hamiltonian Monte Carlo in the case where the potential vanishes. Okay, so we want that this is a lift of this one. Okay, so this Brownian motion has a transition semigroup PT, which is just the heat semigroup, and this has another transition semigroup PT hat. Now, how should the two be related? Well, we cannot expect that they are related for an arbitrary time t, because this was not the case in discrete time either. But we could hope that they are related for small times, because up to some error term, which vanishes as t goes to 0. Okay, so then let's see what we get. So we do the same thing that we did before, but now with pt hat instead of p. So we take integral pt hat f of pi kappa dv. So what's that? Well, this is just the expectation if we start in the point x and in the normal distribution in the velocity of function f evaluated at xt hat, where xt hat is the position of our lifted Markov process. Yeah, so that's just the expectation when we start the lifted process in x and the normal distribution, and then take f of xt hat. Okay, so then in this simple example, we can see how it behaves. So what is xt hat doing? Well, it first has some initial velocity v, and it's starting at x, and then it's just moving to x plus tv before it jumps. After it jumps, it goes, of course, somewhere else. But if we look at small times, then it turns out the jumps will not be relevant for the expansion that we're doing. Okay, as long as it didn't jump, it will be at x plus tv. That means it will be normally distributed with mean x and variance t squared. Now, how does this relate to the Brownian motion? Well, this is the same as the distribution of Brownian motion at time t squared. Yeah, so that's the same as the expectation of Brownian motion starting at x and then of f of xt squared. And of course, here we make some error, but this error turns out to be order little o of t squared, so of higher order. So that means this integral of this lifted semigroup applied to this function depending only on x will be the semigroup of Brownian motion, but now evaluated at time t squared, plus a perturbation term, which is of order little o of t squared. Okay, so that means we do not have the same kind of lifting property as before, but now we have to relate pt hat to pt squared. So there's somehow something replacing the time t by the time t squared, which corresponds to the fact that Brownian motion for small time wiggles around in a different way than your deterministic process. Okay, so now, now we want to rewrite that because since it should only hold for small times, we should be able to rewrite it using generators. So we should be able to express everything through the generators. Okay, so how do we get the generator? Well, here you know this is Brownian motion. So you just take this minus f divided by t squared and let t go to 0, then you get the generator of Brownian motion. Okay, so let's do that. Let's subtract f on both sides and then divide by t squared. So, and then take the limit as t goes to 0. So what do we get? Yeah, on the right, we get the generator of Brownian motion. And on the left, we get this limit here. Now, this looks like a surprise. You may think you have done something wrong now. Because usually, of course, when I want to get a generator here, I have to divide by t and not by t squared. If I divide by t squared, it's much smaller and it will diverge, usually. However, here we're doing some averaging. And turns out that the first order term will disappear by this averaging, and dividing by t squared is really the right thing. That gives you a limit on the left-hand side as well. Yeah, this you can see if you look at this one here. I mean, what is pt hat f of pi minus f of pi? You can just do a Taylor expansion at 0. So then it's just the generator applied to f of pi, well, it's just t times the generator applied to f of pi plus 1/2 t squared, the square of the generator applied to f of pi. That would be Taylor expansion of pt hat up to second order. And since you divide by t squared, you get this expansion here. Okay, and now how can these two things be equal? Well, these can only be equal if the integral of this term vanishes. So we need that the integral of this term vanishes, and then the generator comes up by the integral of the second term. Yeah. So that means this will be our definition of lift in continuous time. So it has two parts. First, the integral of the lifted generator applied to a function depending only on x has to vanish. And then secondly, the integral of the square of the lifted generator. This will give the generator of the collapsed process. Yeah, so that's roughly the definition. We will rewrite it a bit differently because it's not so nice to have here the square, which can lead to technical problems if you have non-differentiable coefficients and so on. Yeah, so we will integrate it and do an integration by parts to write it in a more suitable way, but basically that's the definition. Okay, so now let me give the definition as we give it. So we have a symmetric Markov semigroup PT, can be actually on any space. And then we have another Markov semigroup PT hat on the lifted space. And then we say that PT hat is a second order lift of PT if, first of all, for any function f in the domain of the generator of the collapsed process, f of pi is in the domain of the generator of L hat. And then this integral of L hat f of pi times g of pi d mu hat vanishes for any functions f and g in the domain of L. And then if you take 1/2 the integral of L hat f of pi, L hat g of pi, then you get back your Dirichlet form downstairs, so minus integral FLG. Okay, so this comes from this definition here by just multiplying by another test function g on both sides and integrating with respect to the measure mu. And then you have to bring one of these L hats to the other side. And if it's in many cases, well, if the L hat is antisymmetric, then it's clear you can directly bring it to the other side. But also in the other example we looked at, this L hat is actually something antisymmetric, but plus something that only affects higher order terms, so that you can also rewrite it that way. Okay, so this is once more the definition I gave, written here. And now what do we have for examples? Well, all the processes I introduced to you satisfy this definition. So Hamiltonian dynamics is a second order lift of overdamped Langevin dynamics. Langevin dynamics for any choice of the friction coefficient is a lift. Randomized Hamiltonian Monte Carlo is a lift for any choice of gamma. The bouncy particle sampler is a lift. The zigzag process is a lift. So all these things that have been recently introduced in non-reversible MCMC, they are all lifts of overdamped Langevin dynamics. Okay, so what is it good for? What can we do once we have realized that? Well, what we can do is we can now look at relaxation times. So what can we say about the relaxation times of lifts? And but however, before doing that, there's a problem now. Relaxation time is not so easy in the non-reversible case. If you ask somebody what is the relaxation time in non-reversible case, every person will give you maybe a different answer, which is not the case in the reversible case, because there all answers are the same. Well, they are at least equivalent. Okay, so we use the following definition of relaxation time, which we call the non-asymptotic L2 relaxation time. We just look at the first time where the L2 norm of PT hat of F has decreased by a factor 1 over E for every function F that is orthogonal to the constant functions. Now, of course, the 1 over E you can also replace by some other number. Okay, so you see this is non-asymptotic because after this time you really see this significant decrease in the distance to your stationary distribution. And if you think of Markov chain Monte Carlo, that's really, well, I would say that's really what you like to have, that after a fixed time, you really have this decrease and not just asymptotically as time goes to infinity. So, but now comes the warning. You could think, of course, of many other concepts. First concept would be the asymptotic decay rate or Topler-Punov exponent or whatever it is called. So with which rate does the norm decay asymptotically? This is not the same. A second possibility, you could look at what physicists call asymptotic decorrelation time, or so which is the decay rate of ergodic averages. So if a statistician, the asymptotic variance in the central limit theorem for the ergodic averages, how does it behave? So that's another concept. And actually recently, parallel to our work, appeared a paper by Chatterjee, where he calls this the relaxation time of a Markov chain. So this is yet another concept of relaxation time, which is nice if you want to control ergodic averages. Okay, and then you could also define some spectral gap and define the inverse spectral gap. And also this is yet another concept. So all these are not equivalent in the non-reversible case. So why? So the typical thing in non-reversible case is you have something like this. The L2 norm of your transition semigroup can be bounded by a constant c times e to the minus lambda t. And in the reversible case, the constant c is 1. So it's just bounded by e to the minus lambda t, and then all definitions agree. But in the non-reversible case, no. And so, for example, our relaxation time would be bounded by 1 over lambda times the logarithm of c. And so you see the logarithm of c also comes into play here. So this constant in front comes into play if you look at the non-asymptotic relaxation time. It doesn't matter if you look at the asymptotic rate, which would just be lambda. So in that sense, this concept is somehow like mixing times. So for mixing times, you also look at these non-asymptotic things, and here you do the same for the L2 norm instead of the total variation norm. Okay, so that's our concept of relaxation times. And now there's a nice result. So it has been shown before that for Markov chains, basically you can only improve by a square root, and the same result holds for diffusions. So if PT hat is any second order lift of PT, then the relaxation time of P hat is always greater than 1 over 2 square root 2 times the square root of the relaxation time of P. So the best you can gain is a square root. The corresponding result for Markov chains is a bit different, has been given by Shen, Lovas, and Pak, but they could not formulate it with relaxation times. They had to use some bit strange times called set times. And the reason is they use the proof via conductance, and then they had to, well, conductance is not directly related to relaxation time. And so then they came up with the Z time, and for this, but they got misbound. But here we really get it for the relaxation time as it is defined in this case. And the proof is different as in Chen-Lover-Spack. The Chen-Lover-Spack proof is quite easy. It just says the conductance of the lifted process cannot be better than the conductance of the original process, which is quite clear, and that gives the result. So here we don't use conductance. Here we directly argue with spectral gap, and that's the whole proof, basically. So take any number lambda that's greater than the spectral gap of your generator. So then this means there exists a function such that the Dirichlet form is less than lambda times the squared L2 norm of the function. The function which means 0, of course. And what does this tell you about the lift? Well, now we have this relation. Twice the lifted Dirichlet form is given by this quantity here. This was our definition of lifts. So you see this quantity here is bounded by 2 lambda norm f squared, which is 2 lambda times norm f of pi squared integrated with respect to measure mu hat. Okay, so that means the norm of L hat of f of pi divided by f of pi is bounded by the square root of 2 lambda. And if you let lambda now approach by the gap of L, you see that this quotient here is bounded by the square root of twice the gap of L. And that's true for any function, and then you can take here the, well, no, then you see this infimum here is bounded by the square root. Sorry, it's not true for any function, but this infimum here is bounded by the square root of twice gap of L. And what is this infimum here? This infimum is not the spectral gap. This is what we call the singular value gap. So it's the square root of the spectral gap if you replace L hat by L hat star L hat. And interestingly, again, in this paper by Chatterjee, he also introduced the singular value gap, and it's exactly the quantity that controls the ergodic averages. For us, it's not really the same. We just use it for this bound here, just for the upper bound on the relaxation times. Okay, and if one has this, then one can show, yeah, that the relaxation time. Now I did it the wrong way around. Yeah, no, it's okay. Yeah, sorry, not the upper bound for the lower bound on the relaxation time. Now one can show that the relaxation time is lower bounded by 1 over twice the singular gap. Yeah, I don't give the argument now, but it's not too difficult to prove. You can prove it on half a page. Yes. But this is now only a lower bound, so this is not at all sharp. Yeah. So it's not, the story is not that we now should everywhere replace the spectral gap by the singular value gap, because this is only a lower bound. So it's not like in the reversible case that the relaxation time is really the inverse of the spectral gap. That's not true. Okay, so that gives the result. So with a quite easy proof. And yeah, so that was quite interesting for us because before we had actually tried for a very long time to improve things, to construct things which satisfy better bounds than this. Until I took seriously one of the talks by Werner Kraut, where he said you can never gain more than a square root, and yes, you really cannot. He was absolutely right. Okay, once we have this bound, then we can ask for an optimal lift. Well, it's a bit too much to ask that we really achieve this bound. Actually, if you think about it, it's really not possible, but we can achieve it up to a constant. So we call a lift C optimal if it achieves this bound on the relaxation time up to a given constant C. And now you can look at simple examples where you can make it explicit. So take the Gaussian case. then you find the critically damped Langevin dynamics is 5.46 optimal lift of OLD. So you basically cannot do better than critical Langevin dynamics. So physics has, I mean, nature in physics has really chosen the dynamics that gives you the optimal lift, at least when you choose the gamma the right way. There's a similar result for randomized Hamiltonian Monte Carlo, so it also gives you basically an optimal lift if you choose the gamma the right way. So in both cases, adjusting the parameters the right way, you get the best you can hope for. Okay, so then the question is, of course, can you go beyond the Gaussian case? So can you get also optimal lifts in other cases? And now this is this I cannot do in half a page. This is now a much more tough argument, of course, to really show upper bounds on the relaxation time. But there is a result. So suppose the following, suppose our measure mu satisfies a Poincaré inequality. So that's the base measure. So that satisfies a Poincaré inequality with constant m. And then suppose the Hessian of u is lower bounded by a multiple of m. So it doesn't have to be convex. It can be non-convex, but it has to be lower bounded by a multiple of the constant m.
But the constant m plays what role now?
The constant m, well, it's the constant in the Poincaré.
Okay.
But downstairs for the original process.
Because initially you connected this to convexity, that's where.
Yeah, if you have convexity, then you have Poincaré, but of course it's much weaker because if you have a bounded perturbation and so on, you also have Poincaré. Yeah. Okay, and then the third condition is that the gamma is chosen the right way. That means that gamma is proportional to square root m up to some factor a. So that means you have the critical choice of your friction coefficient in Langevin or of your integration time in Hamiltonian Monte Carlo. And then under these conditions, you see that randomized Hamiltonian Monte Carlo is a C optimal lift of overdamped Langevin with an explicit constant C, which only depends on these values here. Not on M, but only on this A and on this constant C here. And of course, it's not so nice as here. We don't get 5.46. Actually, the number is rather big, 5,000 or whatever. Yeah, but you also see that our proof is quite long and we do a lot of bounds, and it's quite obvious that at many places we maybe lose a factor 2. And then if you lose 10 times a factor 2, you see what constant it gives. Yeah, so it might well be that even here we are close to optimality. We don't know. Yeah. Okay, then you have a similar result for Langevin dynamics, which can be basically proven the same way. And the proof is really already done to large parts by Lu and Wang and Xiaolu Wang. And yeah, what we did is we redid their argument, and we could do it a bit simpler using the concept of lifts. So some points we could simplify. And also we could improve certain points a little bit, but basically in the Lu Wang and Xiaolu Wang paper, the result is already there. And so how does the argument work? Well, the key is a new technique, a new analytic technique that has been introduced by Albritton, Armstrong, Murat, and Novak. So there's the classic hypocoercivity approach in analysis, because we have here a diffusion process or processes with degenerate noise, and where noise is only acting in the velocity variable. So we are in hypoelliptic situations. So you need quantitative bounds in hypoelliptic situations. And then there has been the approach by Villani and then Dolbeau, Muru, Schmeiser, and so on, who derived so the so-called hypocoercivity approaches who derived such bounds. But with these bounds, you could not show that you get an optimal lift or a C-optimal lift, because just at the critical point, these bounds were not good enough. And the first result that came up with that led to a bound that was good enough was this paper by Bertrand, Armstrong, and Novak. And that it can be used to get this bound of the right order. This has been shown by Lu and Fang. And so what is the approach based on? Well, it's based on space-time Poincaré inequalities. So it's not enough to look at space only, but you now have to average over time intervals. And then there's a concept of space-time Poincaré inequalities. So you really have to think of it as a process in time and space. And then you can use this concept together with something that's in analysis called the divergence lemma or Lyon lemma. And then you can apply that to prove such bounds, which is still quite a lot of things to do, but it's now somehow transparent framework that is available on which you can, which allows you to get such bounds in such situations with degenerate noise. And I think for the future, it still offers a lot of possibilities. I think it's the right framework to look at in the future if one wants to say something about bounds in these non-reversible situations. Yeah, I think I will not give you the technical details of this here, but because this would now be too long and not the purpose of this talk. But if you're interested in that, of course, we can talk about it afterwards. Okay, now I think I will stop here.
Any questions?
Thanks, that was a great talk. So I guess the canonical kind of example of lifts here that you were running with was the case where you think of the added variables as a kind of velocity term. I guess another one is kind of tempering style heuristics, where you think of the added terms as like a temperature variable. And there you can sometimes get much like in cases like mixture of two Gaussians with well-separated modes, like a tempering like change can get a much better speed up than a square root. Like from exponential in the distance squared, it can get to like poly in the distance between the modes. So what goes wrong, I guess, like how does this framework not catch these types of lifts?
Yeah, I'm not sure. I haven't thought about it from that point of view. Yeah, it would be interesting to look at. It may well be that it's just something else, not the same that you do here. But yeah, it's a nice idea to think about it. Can also be written.
Thank you. Is there a similar theory for the loxable length case?
Very good question. We'd like to have, yeah, so far there's not. We tried a bit. It's not easy. I think analysts tried even more than we did. So far, it has not been successful, but that would be certainly great to have this next step.
We have other questions? If no,
Can I ask one more question? How does this relate to the discretization? If I know that the under Mangiovanni is a lift of overdamped, and if I discretize both of them, can I say that the discretization is also a lift of the other one?
Yeah, I mean, what our definition gives is that for small t, it's somehow behaving as a lift up to this order little o of t squared error term. Of course, discretization you always run about on a finite time interval. And ours is just saying about infinitesimal. So we can only say that it's a lift up to this error term of order little o of t squared. So if your discretization is fine enough, then up to this error term you can have it.
Okay, thank you.
It's like speaker can